what we're going to be looking at is LeChatlier's principle and how it affects products, reactants in equilibrium. Okay, so why do we care where the equilibrium will shift? Okay, well, it's really important in like manufacturing of chemicals because you want to have more of your product, right? You want that equilibrium to be to the right because whatever product you're making, you want to get the maximum amount of it so that you can make the most money off of it. So there's several different factors that are going to affect your equilibrium. Okay, changes in concentration, changes in pressure, and changes in temperature are all ways that equilibrium can be altered. And so whenever you're dealing with manufacturing, those considerations must be made so that you can maximize the yield of your products. So LeChatlier's principle states that if a system at equilibrium is changed or altered or disturbed by a change in one of the features or one of the factors, such as temperature, pressure, or concentration, basically the system is going to adjust and change so that equilibrium can be restored against that disturbance. So let's go ahead and check out the change in concentration factor associated with LeChatlier's principle. Okay, so basically, if you add a component, you're going to shift away from whatever side you've added that component to. So if you add a product, you're going to shift away from products and towards reactants. If you add a reactant, you're going to shift towards products. Obviously, the same concept is true as if you remove something. You're going to shift towards the side that you remove that component from. So if you remove a reactant, you're going to produce more reactants. If you remove a product, you're going to produce more products. Okay, so something though to note is that only species that affect K are going to shift equilibrium. Okay, so if your content or your equilibrium expression doesn't have the component that you're adding or subtracting in it, it's not actually going to affect your shifts in equilibrium. So let's go ahead and let's look at the following reaction here. Okay, basically they want us to take this reaction and predict the shift of equilibrium based on the addition of various items. Okay, so you may want to first write your equilibrium expression. So what I would do is I would write my equilibrium expression with respect to concentration. Okay, I would write it as follows. Okay, and notice I've excluded the two reactants that are present, and the reason why I've excluded them is simply because this is a heterogeneous setup, and obviously we don't include the solids in that equilibrium expression. Okay, so let's go ahead and let's look at the addition of CO. Okay, CO is part of the equilibrium expression. Okay, it is a product, so if I add more product, that means that I'm going to shift away from the thing that I added, so it's going to shift it towards reactants. Okay, so basically we're going to shift towards reactants if I add more CO to their container. Okay, what's going to happen if I add or remove the carbon or the AS4O6? Okay, once again, those are not components in the equilibrium expression. Okay, so adding or removing them is not going to affect your equilibrium shift. Okay, so no change. Okay, and if I remove AS4, okay, it is in the equilibrium expression. If I remove that, okay, basically what's going to happen is my reaction is going to shift towards the product side because I've removed that product. So basically, if you think about what's actually involved in the equilibrium expression and you consider if something's been added or taken away, you can figure out the shift that's going to occur. Okay, so something I do want to mention is that even though carbon and the AS4O6 are not included in the equilibrium expression, they are being used or produced during any shifts that occur. Okay, so just because they don't affect the equilibrium position, if they're changed, they will change in terms of quantity. So if we shift towards reactants in this case, obviously we're going to produce more AS4O6 and carbon solids. Okay, or if we shift towards the right, towards products, obviously we're going to use up some of those reactants in order to produce additional products. So please be cognizant of the fact that just because they don't show up in the equilibrium expression doesn't mean that their amounts aren't necessarily changing. So changes in pressure with respect to LeChatelier's principle. There's basically three ways in which you could change a pressure, the pressure of a container. Basically adding or removing gaseous components. So basically if you add a reactant that's gaseous or subtract out a product or reactant that's gaseous, that's going to affect the shift much in the same way that we saw earlier. Okay, 2, you could also add an inert gas. Okay, and if you add an inert gas, obviously it's not part of the equilibrium expression, so it's actually not going to shift your equilibrium. Okay, and the last option is to change your volume. Okay, so when you decrease the volume of your container, the system actually reduces its volume by actually decreasing the total number of gaseous products. So basically, if you have an increase in pressure or a decrease in volume, you're going to have a shift to the side with the least number of gaseous molecules. So looking at an example here, basically we have this reaction, okay, with all of these gaseous molecules. And basically they want to know what direction the equilibrium is going to shift if we increase the pressure on the container holding these two. Okay, so increasing the pressure is basically can be looked at as a decrease in the volume. If you decrease the volume, the equilibrium is going to shift towards the side with less molecules of gaseous reactant or product. So in this case, I have 4 equivalents of gaseous reactants, and on this side I have 2 equivalents of gaseous product. Okay, so the side with less gaseous molecules is actually the product side. So increasing the pressure is going to increase the synthesis of ammonia. So you'll get more product if you increase the pressure of this reaction. If we look at the reaction here, okay, and we've reduced the volume, they're asking us which way will the equilibrium shift. Okay, so in the situation of reducing the volume, it's similar to increasing the pressure. Okay, so on this side we have 6 gaseous components. On this side we don't have any, so we're going to once again shift over to the right to produce more products and to reduce the number of gaseous molecules that are present in that container. Okay, so our change in temperature with respect to LeChatelier's principle requires us to take a small step back and analyze how the constant changes. So pressure, concentration, those types of changes affect your equilibrium position, okay, but do not affect the constant. The only thing that's actually going to affect the constant's value is the temperature at which the reaction is occurring. Okay, so the changes that you're going to see, or the shifts that you're going to see, are going to depend on whether your reaction is exothermic or whether it is endothermic. Okay, and we're going to look at the heat produced or the heat absorbed by a specific reaction as, reactants or products for those specific examples. So if we look at this example that they gave us here, they told us that this is an endothermic process. So what that means is that this process needs to absorb heat in order to occur. So if we go ahead and look at heat as being a reactant in this case, if I add more heat to the reaction, okay, by increasing the temperature on the hot plate or the Bunsen burner, okay, I'm actually increasing the amount of reactant that I have. If I increase the amount of reactant, okay, equilibrium is going to shift to the right towards your products. Okay, if I cool this reaction, basically that's the equivalent of removing heat. If I remove this reactant, equilibrium is going to shift towards reactants or to the left. Okay, so basically, depending on if you have an endothermic or exothermic reaction, you basically look at how the addition of heat or subtraction of heat would shift that equilibrium, just like any other reactant or product that's involved in the equilibrium expression. Okay, so this is a nice visual example of how an endothermic reaction can change depending on what you place it in or what kind of temperature conditions you run the reaction under. Okay, so this cobalt water complex here is actually pink, okay, and this cobalt chloride complex is actually blue. Okay, so whenever I move towards the right and I produce that bluish color, that means I'm producing this product. And if I'm in the pink range, that's obviously meaning that I am moving towards the reactant side. So now in this case, they told us this is endothermic. So once again, heat is going to be on the reactant side. Okay, so in the conditions where, I have room temperature, okay, that's going to be our comparison point. If we take this reaction and then increase it, or at least increase the temperature, we warm up the container, that means that I am adding more reactant. If I add more reactants, the equilibrium shifts towards the right, or towards products. If I shift towards products, obviously the product that I'm anticipating getting is blue, and notice we've gone from blue to very, very blue. Okay, in that same concept, or same thought process, if I cool this reaction, okay, basically cooling this reaction, I'm therefore removing heat, which is a reactant. In this case, my equilibrium is going to shift to the left towards the pink cobalt water complex, and subsequently we see the production of a pink solution. So this is a nice visual to help you guys see that the pink and blue shifts that will occur depending on the addition or subtraction of heat. Now, obviously, if we were dealing with an exothermic reaction, heat would be over here on the product side, and we would use this same thought process to figure out how the addition or removal of heat would affect your equilibrium. Okay, so please understand that a catalyst has no effect on equilibrium position. Okay, so your catalyst is responsible for increasing the rate at which equilibrium is achieved. So it will speed up the process, but it doesn't actually change the composition of the equilibrium mixture. Okay, so it just makes it easier for equilibrium to be reached by lowering that activation energy, okay, as we've discussed before, but it does not actually affect the equilibrium position itself. Okay, it's only going to speed up the process.